Welcome to our countdown of 10 true facts you won't believe. Get ready to have your mind blown as we dive into the strange, surprising, and downright unbelievable realities of our world.
The idea that bananas are berries but strawberries aren't stems from the botanical definitions of these fruits, which differ from everyday usage. In botany, a berry is a type of fruit that develops from a single ovary of a flower and typically contains multiple seeds embedded within its fleshy interior. Examples of true berries include bananas, grapes, and kiwis. Bananas fit this definition because they form from a single ovary and have a soft, fleshy interior with seeds, even if the seeds are tiny in cultivated varieties. Strawberries, on the other hand, don't qualify as berries by botanical standards. They are considered aggregate fruits because they develop from a single flower with multiple ovaries. The small, seed-like structures on the surface of a strawberry are actually individual fruits called achenes, each containing a single seed. The fleshy part we eat is an enlarged receptacle, not the fruit itself. This distinction highlights how scientific classifications can differ significantly from common perceptions. Many fruits we colloquially refer to as berries, such as raspberries and blackberries, also fail to meet the botanical criteria as they are aggregate fruits. Meanwhile, fruits like bananas and tomatoes, which we don't usually think of as berries, fit the definition perfectly. This discrepancy can surprise many people and demonstrates the fascinating complexity of plant biology.
Water can boil and freeze simultaneously under a specific set of conditions known as the triple point. This phenomenon occurs when the temperature and pressure are such that water exists in equilibrium as a solid, liquid, and gas. For water, the triple point is at a precise temperature of 0.01 degrees Celsius, 32.018 degrees Fahrenheit, and a pressure of 611.657 pascals, 0.00604 atmospheres. These conditions are highly specific and not typically encountered in everyday life. At the triple point, the energy being added to the water is perfectly balanced among the three phases. As heat enters the system, some water molecules transition into vapor, boiling, while others form a crystalline structure, freezing. This equilibrium is a direct result of the unique molecular properties of water and the precise interplay between pressure and temperature. The triple point is significant in both scientific and practical contexts. It serves as a reference point for calibrating thermometers and is a critical concept in thermodynamics. Furthermore, understanding the triple point of various substances is essential in fields like meteorology, engineering, and material science, where phase changes influence real-world phenomena. For example, in a laboratory, achieving the triple point of water involves carefully controlling the environmental conditions using specialized equipment. Observing the coexistence of ice, liquid water, and vapor at the triple point provides a striking visual representation of the intricate balance governing phase transitions.
The fax machine, or facsimile, was a groundbreaking invention patented by Alexander Bain in 1843, well before the telephone became a reality. Bain, a Scottish clockmaker and inventor, devised a method for transmitting images using synchronized pendulums, making it the world's first device capable of electronically reproducing documents. His invention was rudimentary compared to modern fax machines, but it laid the foundation for future advancements in telecommunications and imaging technology. Bain's device worked by scanning an image line by line with a stylus. The machine would convert the visual information into electrical signals, which were then transmitted to a receiver. The receiver in turn recreated the image using a chemically treated surface. Although the process was slow and the quality of the transmitted image was limited, the principles of scanning and encoding information in this way remain central to modern faxing. This innovation predated the telephone by over 3 decades, highlighting the visionary nature of Bain's work. It was a precursor to the development of more sophisticated fax machines, which would only gain widespread use in the 20th century, especially with the advent of telephone networks. Bain's invention demonstrates how early technologists imagined ways to bridge distances and share information long before many of the tools we take for granted today were even conceived.
The immortal jellyfish, known scientifically as Turritopsis dohrnii, is a remarkable marine creature capable of defying the aging process. Found in oceans worldwide, it is renowned for its extraordinary biological ability to revert to an earlier stage of its life cycle under certain conditions, effectively allowing it to escape death by natural aging. While this doesn't mean individual jellyfish live forever in a practical sense, their potential for indefinite regeneration is unique in the animal kingdom. The life cycle of Turritopsis dohrnii begins like other jellyfish, as a free-swimming larva called a planula. The planula eventually settles on a surface, such as a rock or seabed, and develops into a polyp. From the polyp stage, it buds off into multiple medusae, which are the adult jellyfish we typically recognize. Unlike other species, when faced with stress, injury, or unfavorable environmental conditions, an adult Turritopsis dohrnii can transform its cells to revert to the polyp stage, starting its life cycle anew. This process, known as transdifferentiation, involves the reprogramming of specialized cells back into stem cells, which can then develop into new types of cells needed for the polyp structure. This ability has drawn significant attention from scientists studying aging and regenerative medicine. Understanding the genetic and molecular mechanisms behind the jellyfish's transdifferentiation process could provide insights into reversing cellular aging and developing therapies for degenerative diseases in humans. However, while theoretically immortal, Turritopsis dohrnii is not invincible. It can still fall prey to predators, disease, or environmental threats. The existence of Turritopsis dohrnii serves as a profound reminder of nature's complexity and the untapped potential within biological systems. Its unique life cycle challenges traditional notions of life and death, offering a glimpse into the possibilities of biological regeneration and longevity.
The statement that a teaspoon of honey is the lifetime work of 12 bees highlights the immense collective effort that honeybees undertake to produce even a small quantity of honey. This insight into the industrious lives of honeybees underscores the complexity and efficiency of their social structure and the vital role they play in ecosystems. Honey is produced by worker bees, which are all females, during the active foraging seasons of spring and summer. These bees collect nectar from flowers, a sugary liquid that serves as the raw material for honey. A single bee typically visits between 50 to 100 flowers in one foraging trip, collecting only a small amount of nectar each time. Over its lifetime, which lasts around 6 weeks during peak activity, a worker bee produces just about 1/12 of a teaspoon of honey. This means it takes the collective efforts of 12 bees working tirelessly to fill a single teaspoon. The process of honey production is meticulous and highly organized. Once nectar is gathered, it is stored in the bee's honey stomach, a specialized organ separate from its digestive system. Enzymes in the stomach begin breaking down the nectar's sugars into simpler compounds such as glucose and fructose. Back at the hive, the bee regurgitates the partially processed nectar into the cells of the honeycomb, where other worker bees fan it with their wings to evaporate excess water, concentrating the nectar into the thick golden substance we know as honey. The honey is then capped with beeswax to preserve it for future use as a food source for the colony. And this extraordinary production process is not only a testament to the teamwork and efficiency of honeybees, but also to their critical role in agriculture and ecosystems. While producing honey, bees pollinate a vast array of crops and wild plants, supporting biodiversity and food production worldwide. However, the scale of their effort also highlights their vulnerability. Declines in bee populations due to habitat loss, pesticides, climate change and disease have raised concerns about the sustainability of this essential process. Recognizing the sheer labor behind each drop of honey emphasizes the importance of protecting honeybee populations. Their work, while seemingly small on an individual level, contributes significantly to ecological balance and human food security.
The idea that if you shuffle a deck of cards, it's almost certain that the resulting order has never existed before is based on a concept in probability and combinatorics. This fascinating fact stems from the astronomical number of possible arrangements, or permutations, of a standard 52-card deck. The number of these permutations is given by 52 factorial, which is the product of all integers from 52 down to 1. 52 factorial equals 52 times 51 times 50 times, and so on, down to 2 times 1. The result of this calculation is approximately 8.0658 times 10 to the power of 67, a number so vast that it defies ordinary comprehension. To illustrate how large 52 factorial is, consider the following comparisons. The estimated number of atoms in the observable universe is around 10 to the power of 80. The number of card permutations, though smaller, is of a similar magnitude. If every person on Earth, around 8 billion people, shuffled a deck of cards once per second since the beginning of the universe, about 13.8 billion years ago, they wouldn't come close to generating all possible permutations. This astronomical number means that each shuffle of a deck is incredibly likely to produce a sequence of cards that has never existed in the history of the universe. Even if every deck of cards ever shuffled by humans since the invention of playing cards were accounted for, the total would still represent only a minuscule fraction of the possible permutations. Each card in the deck has an independent position relative to the others, and the number of combinations grows exponentially as more cards are added. This rapid growth in permutations is a fundamental characteristic of factorial mathematics, making the number of unique arrangements practically infinite on a human scale. Practical implications. While it's theoretically possible to repeat an arrangement, since 52 factorial is finite, the chances of it happening randomly are so low as to be negligible. The randomness introduced by a proper shuffle ensures a near total uniqueness of the order every time. This has practical applications in games of chance, where shuffling creates fairness by making outcomes unpredictable. A reflection on probability and uniqueness. The realization that each shuffled deck represents a likely one-of-a-kind order is a humbling reminder of the vastness inherent in combinatorial mathematics. It invites us to appreciate the concept of infinity in a tangible way, transforming an ordinary activity like shuffling cards into an encounter with the extraordinary.
Your stomach's ability to function without digesting itself is one of the marvels of human biology. This is made possible by its extraordinary capacity to regenerate its lining every 3 to 4 days. This rapid turnover is crucial because the stomach lining is constantly exposed to highly acidic gastric juices and digestive enzymes, both of which are powerful enough to break down food and potentially the stomach's own tissues if left unchecked. The stomach plays a critical role in digestion by secreting gastric juices composed of hydrochloric acid and digestive enzymes like pepsin. These substances are essential for breaking down proteins into smaller peptides and preparing food for absorption in the intestines. However, the hydrochloric acid is highly corrosive, with a pH as low as 1.5 to 3.5, comparable to battery acid. Additionally, pepsin is a protease, an enzyme that digests proteins, which includes the proteins that make up the stomach's own tissues. To prevent self-digestion, the stomach has several protective mechanisms. First, the mucus layer. The inner lining of the stomach is coated with a thick layer of mucus, which acts as a physical barrier. This mucus contains bicarbonate, which neutralizes stomach acid near the stomach wall, protecting it from direct contact with the corrosive environment. Next, tight junctions. The cells of the stomach lining are tightly packed together, forming a strong barrier that prevents gastric juices from leaking into deeper tissues. And lastly, regeneration. Despite these protections, the harsh environment of the stomach causes significant wear and tear on its epithelial cells. To counteract this, the stomach regenerates its epithelial lining every 3 to 4 days. This rapid cell turnover ensures that damaged or dead cells are replaced promptly, maintaining the integrity of the stomach wall. The regenerative process is driven by stem cells located in the stomach's gastric glands. These stem cells divide rapidly, producing new epithelial cells that migrate upward to replace the worn-out ones lining the stomach. This continuous cycle ensures the stomach remains functional and intact despite the constant assault of acid and enzymes. When the stomach's protective mechanisms fail or are overwhelmed, conditions like gastritis, which is the inflammation of the stomach lining, or peptic ulcers can develop. These occur when the acid damages the stomach tissue, often exacerbated by factors like Helicobacter pylori infection, prolonged use of non-steroidal anti-inflammatory drugs, excessive alcohol consumption, or stress. In severe cases, untreated ulcers can lead to perforation of the stomach wall, which is a medical emergency. The stomach's ability to continuously rebuild itself highlights the precision and resilience of the human body. The balance between the destructive forces of digestion and the protective mechanisms of regeneration ensures that the stomach can perform its vital role without succumbing to its own power. Understanding this process not only sheds light on how the stomach works, but also emphasizes the importance of maintaining good gastrointestinal health.
The inability to burp in space is a peculiar and fascinating consequence of microgravity, the condition of near weightlessness experienced by astronauts in orbit. On Earth, gravity plays a crucial role in the functioning of the digestive system, particularly in separating gases from liquids and solids in the stomach. In space, the absence of gravity disrupts this process, making burping as we know it virtually impossible. Under normal conditions on Earth, when you swallow food, liquid, or even air, your stomach fills with a mixture of solids, liquids, and gases. Gravity causes these components to settle into distinct layers. Liquids pool at the bottom, solids mix in the middle, and gases rise to the top. When gas builds up in your stomach, the esophageal sphincter, a muscular valve at the top of the stomach, relaxes to allow the gas to escape as a burp. This separation ensures that only gas is released, leaving liquids and solids in place. In the microgravity environment of space, this natural separation of stomach contents doesn't occur. Instead, the gas, liquid and solid components mix into a homogeneous slurry. If an astronaut tries to burp in space, the gas cannot escape independently because it's trapped within this mixture. As a result, attempting to burp often leads to what astronauts call a wet burp, where both gas and stomach contents are expelled simultaneously, essentially a small regurgitation. This phenomenon is one of the many adjustments astronauts must make when living and working in space. To minimize discomfort, astronauts are advised to eat and drink carefully, avoiding behaviors that might introduce excessive air into the stomach. The design of space food and beverages also takes this into account. Carbonated drinks, for instance, are generally avoided because they can cause excessive gas buildup, which becomes particularly problematic in microgravity. The inability to burp in space may seem like a minor inconvenience, but it underscores the profound impact of microgravity on human biology. Many bodily functions that are routine on Earth become more complex in space, requiring careful management to ensure astronaut comfort and health. As space exploration advances and missions grow longer, understanding and mitigating such challenges will become increasingly important. This quirky fact about burping also serves as a reminder of how much we take gravity for granted in everyday life. On Earth, gravity effortlessly orchestrates countless processes in our bodies that we rarely notice, until they stop working the way we expect.
The idea that there are more stars in the universe than grains of sand on all the Earth's beaches is a breathtaking reflection of the scale of the cosmos. This statement, often attributed to astronomers like Carl Sagan, is not only poetic but also rooted in scientific reasoning and estimations. It emphasizes the vastness of the universe and the humbling realization of humanity's small place within it. To understand the comparison, consider the number of grains of sand on Earth's beaches. While it's impossible to count every grain directly, scientists estimate that there are roughly 7.5 times 10 to the power of 18, or 7.5 quintillion grains of sand on all the beaches of the world. This estimate is based on the average size of a grain of sand, the depth and width of sand layers on beaches, and the total area of sandy coastlines. The number of stars in the observable universe is even more staggering. Our galaxy, the Milky Way, alone contains about 100 to 400 billion stars. The observable universe is estimated to contain about 2 trillion galaxies, many of which are similar in size to the Milky Way, while some are even larger. Multiplying the number of stars per galaxy by the estimated number of galaxies, astronomers arrive at a figure of approximately 1 times 10 to the power of 24 stars, 1 septillion stars. When comparing 10 to the power of 18 grains of sand on Earth to 10 to the power of 24 stars in the universe, it becomes evident that the number of stars far exceeds the number of sand grains. To put it in perspective, for every grain of sand on every beach, there are likely around 1 million stars in the observable universe. This comparison only considers the stars in the observable universe, which is limited to what light has had time to reach us since the universe began, about 13.8 billion years ago. The total universe may be far larger, potentially infinite, containing an uncountable number of stars. If this is the case, the disparity between stars and grains of sand would be even greater. This comparison inspires a profound sense of awe about the scale of the universe. It underscores the limitations of human comprehension when faced with astronomical numbers and distances. While grains of sand are tangible and familiar, stars are distant and mysterious, yet they both serve as metaphors for the sheer abundance of the cosmos. The phrase also reminds us of the interconnectedness of the universe. Grains of sand are formed by processes like erosion and weathering on Earth, while stars are born from the collapse of cosmic gas clouds in faraway galaxies. Both represent the outcomes of natural processes that occur across vastly different scales and timescales. This comparison is more than just a fact. It's a gateway to deeper curiosity about the universe and our place within it, encouraging both wonder and humility.
The statement, "A bolt of lightning is 5 times hotter than the surface of the sun," captures the astonishing intensity of lightning, one of nature's most dramatic phenomena. This comparison emphasizes the incredible energy involved in lightning strikes and the unique physical conditions they create. A typical bolt of lightning can reach temperatures of approximately 30,000 Kelvin or 53,540 degrees Fahrenheit or 29,727 degrees Celsius at its core. This extreme heat is generated in an instant as electrical energy travels through the air, ionizing it into a plasma, a state of matter where electrons are stripped from atoms. This ionization process, combined with the immense electrical discharge, creates the extraordinary temperatures associated with lightning. By contrast, the surface of the Sun, known as the photosphere, has an average temperature of about 6,000 Kelvin or 10,340 degrees Fahrenheit or 5,727 degrees Celsius. This is considerably cooler than the temperatures reached in a lightning strike. However, it's important to note that the Sun's core is far hotter, around 15 million Kelvin, due to nuclear fusion processes. The extreme heat of lightning is a result of the immense electrical energy involved in its formation. A lightning strike typically occurs when a build-up of electrical charge in a cloud seeks to equalize with the ground or another part of the cloud. When this charge difference becomes great enough, a rapid discharge occurs, sending a current of up to 100,000 amperes through the atmosphere. This sudden flow of electricity heats the surrounding air to tens of thousands of degrees Kelvin in a fraction of a second. The incredible heat of lightning has a range of effects. Thunder. The rapid heating and subsequent expansion of the air around the lightning bolt create a shockwave which we perceive as thunder. Light. The heat ionizes the air, producing the brilliant flash of light associated with lightning. Material effects: lightning can melt or vaporize materials it strikes, including sand, which can fuse into glass-like structures called fulgurites. Trees struck by lightning often explode or catch fire due to the intense heat and sudden vaporization of internal moisture. While a lightning bolt's temperature exceeds that of the sun's surface, the comparison is limited by the vastly different contexts. The sun's surface maintains its temperature consistently across an enormous area fueled by nuclear fusion, whereas the extreme heat of lightning is localized and fleeting, lasting only microseconds. Awe-inspiring energy. The fact that a transient bolt of lightning can momentarily outshine the surface heat of our sun highlights the extraordinary energy present in Earth's atmosphere. It's a reminder of the power of natural phenomena and the intricate physics at play in the world around us. Understanding the properties of lightning not only deepens our appreciation of its beauty and power, but also underscores the importance of respecting its dangers. Its extraordinary heat, combined with its electrical force, makes it a phenomenon to marvel at and approach with caution.
Thank you for watching. We hope these mind-blowing facts left you amazed and inspired. Don't forget to like, subscribe and hit that notification bell because there's plenty more where that came from. Stay curious and we'll see you in the next one.